Gaussian based classifier and a little bit of theorem about generative versus discriminative classifier. Today, we're still in the classification to continue the naive based classifier we finished last time. So last time I did a very detailed explanation about how to learn and how to test naive based classifier. So actually it's covered almost everything you need to understand how to work on your homework 5. So I hope you enjoy homework 4. So it's a very good learning about carriers. If you have never learned about deep learning platform before, it's also a fairly easy and nicely documented library. So if you did deep learning research before, so maybe this is too easy to you, but try to maybe win the competition. So because you're so experienced, right? Let's see how can you do this submission, try to maybe win in the leaderboard. So last year, there's a student was so much better than the other students, and I'm pretty sure she did not do some other tricks. It's a very good solid win last year she did. But anyway, I'm not going to share the trick because there's too many tricks, and there are many tricks online. Of course, there's also a lot of strategies maybe you can use from the library or maybe learn from blogs. So this is a very good homework. Kind of open the door of it's a fairly easy toy data. So no matter how, but in the end, this is a pretty small and toy data. Okay, so let's come back to a little bit vintage kind of classifier is the Bayes classifier. But actually, even though the state-of-the-art majority are deep learning driven, but naive Bayes classifier has been contributed, has been a very important prediction model handling the language data. So I want you to understand, hopefully, to maybe even compare. So understand why we used to, or the majority of natural language processing or text analysis use naive Bayes before, why now using the deep learning. But even for now, not every problem fits the deep learning. And there are a very big group of problems still the Bayes classifier, naive Bayes, or a little bit revised version still could fit really nicely. Okay, so but today actually I'm going to not talk about discrete type of Bayes classifier, but instead the Gaussian Bayes classifier, and it's very classic statistical model called LDA and QDA. So these two models are very important classification models. Which normally talk about or people focus on in the statistical community, and they are they are related nicely to the one we just covered during last week. Then by the end, I'm going to discuss a little bit about comparing discriminative classifier versus generative classifier. So at what situation discriminative classifier works better and why it works better? At what other situations generative classifier works better and why better? Oh, sorry. All right, so this is the summary of what we are covering about generative Bayes classifier. So in summary, we're always using the MAP rule and to use the joint probability PXC and then decompose it using the chain rule to through the PX conditional C times PC, which is the prior. And the differences of different generative Bayes classifier differ in how they model the PX1 on P conditional C. What we covered last time is the naive discrete classifier, which trying to capture a specific value of a feature exists or not. And then you actually use a multimodal distribution to represent it, and then using the cons to estimate the multimodal parameter from the training data. So then let's go to the continuous random variable. So this is actually a review. I did not get into a review during when we tried to do the probability. So the continuous random variables, instead of using probability mass function, we're using the probability density function to represent its distribution. And the probability density distribution describes the probability density, of course. And then there's a few axioms about probability PDF, probability density function, which you should already learn in your probability entry level class. So first of all, the PDF is supposed to be positive or non-negative. The integral of a PDF is supposed to be 1. And this is, in fact, it has this one-to-one analogy to discrete random variables. So over all the possible values of a discrete random variable, the summation of probability mass function is supposed to be 1, right? So this has a one-to-one mapping there. So here, instead of doing the summation, we are doing the integral. So the majority of the differences of discrete random variable versus the continuous random variable, it's almost just this. Convert the summation formulation into the integral formulation. If you want to obtain the probability of a range of values, you normally just do the integral of that specific region. So for example, you want to understand what's the probability maybe of this x variable, which is continuous between 5 and 6, you just do the integral from 5 to 6, and then on top of the PDF, that density function. So, and then how to calculate mean and variance of continuous variable, which is actually also almost the same. So in the discrete case, to calculate mean, we actually do VI, Px equals to VI for that specific values. We just convert that summation into an integral in the continuous case. Nothing special. And if you want to calculate the expectation of a function on my x variable, it's the same thing. You just do an integral by replacing the x into gx, and then times the fx dx, which is the PDF, then over the dx. So you already learned all this hopefully in your probability class. And very importantly, also the other statistics is the variance of a random variable. Variance of a random variable in the end just the ex minus mu quadratic. And in the discrete case, you just replace x minus mu quadratic as that g function here, and then you sum over all the possible values of which is the vi. And in the continuous case, do the same thing. Just replace the summation into integral. And then here is the probability mass function, and you replace it into a probability density function. And totally the same, just summation into integral operation. And covariance, covariance is, so variance capture how wild your data distributed apart from the mean, right? That's the variance capture. How wild, how different my mean, my random variable apart from my mean. And covariance is about a pair of variables. How do their values related to each other or correlated to each other? So this is captured through this equation with E x times y, this is a new random variable, times its its expectation, minus mu x times mu y. All right, so the most classic continuous random variable is the Gaussian distribution. So let's look at a single case. a single Gaussian distribution, it in the end has a bell shape of PDF. And this bell-shaped PDF is normally written as this math n with two parameters. First parameter is the mu, which is the mean. Second parameter is the sigma square, which is the variance. So it really tells you a Gaussian distribution is fully determined. It's fully determined. Its probability density function is fully determined by its the mean and the variance values. And this is the PDF of that of the Gaussian distribution, which I think you should also already learn. This is almost the thing you normally focus on in the probability entry, or maybe probability 1. It's about Gaussian and PDF, how the PDF look like, how the sigma changes the wildness of the distribution. So this has a really sharp peak in the middle. So what do this sharp peak in the middle even mean here? Give me a rough guess. So what do this PDF has a peak indicate? So this is probability density function, right? It's really trying to show you how the data, how the X distributed. And when there's a peak in that mean position, it essentially tells you what? So if I'm sampling data from this Gaussian distribution, the majority of the sample will locate close to the mean. That's exactly what this distribution function is trying to tell you. The majority of the X, if I'm sampling from this Gaussian distribution, the majority of the X, because if you still remember, this represents the likelihood, right? How likely a X locate. The majority of the X locate close to the mean position, which means the density here, there are many X. If I'm doing the sampling from this distribution, the majority of those samples are closely locating around that position. And there are much fewer number of positive samples close to the two tails, to the left tail or the right tail. So you can give an example is the mean height of the height. For example, the people's height, it's maybe use men's height and women's height are actually two different Gaussian distributions. The men's height, the majority maybe in 6. Yeah, I'm just guessing. And their smaller number, the grown-ups. The smaller number is maybe shorter than 5, and there's smaller number of higher than 7. That's roughly just it trying to tell you. Yeah. Okay, so that's about this. And then this is one dimension, right, which is only one feature, like only height. But when you're trying to represent maybe a subject, maybe a patient, only the height is not enough, right? You have age, maybe blood pressure, or sugar levels, all different type of variables. How do you represent it, and then into a multi-dimensional case? So then this comes the multivariate Gaussian distribution, which has a pretty complicated PDF formula. So now our X is not just a scalar anymore, it's a vector. So there are multiple features here. So x1 onto xp. So it's a relatively more complex formula compared to we learned before, but it's still pretty relatively easy. So this part is actually about the covariance matrix. The sigma here, mu is our mean vector. The large or the capital sigma is our covariance matrix. It's the covariance matrix. And then the map vector this vector has the size p times 1, which is the same size as your feature dimensions, and the sigma matrix is p times p matrix. It essentially, as if you still remember, the diagonal is each features its own variance. And the off-diagonal terms capture the covariance of an ith variable and a jth variable. So it's really just that covariance of xi and xj variable at ith and j's position. So the whole probability density function of a multidimensional Gaussian distribution is also fully captured by, if you know its mean vector and you also know its covariance matrix. It's fully determined by these two parameters. So that means to be able to learn learn this probability fx PDF, what you really need to estimate is only two things. One is the mean vector, the other is the covariance matrix, which has p plus p times p number of parameters. So the number of parameters to estimate a Gaussian distribution from data is p plus p quadratic from data. It's the size of the parameter to estimate. All right. So honestly, if we do some one-to-one analogy to what we learned before, so if you still remember the discrete case, in the discrete case, the number of parameters you need to estimate is related to each discrete variable's the number of possible values. So assuming those k, that's a k. So let's just do a little bit of review. The discrete p x1, this is a probability mass function from data. So we actually have a conditional C, but in this case we don't condition on the C yet, we only just write the joint probability. So if we only write as a joint probability, we don't, just for now, don't consider condition on a C specific class. The number of parameters, last time we actually reviewed the non-naive version versus a naive version. Because you just did your quiz, so you suppose already did the homework. So the non-naive version, how many parameters you need to estimate for the non-naive version. So assuming each variable, there's only two possible values, exist or not exist. So how many parameters for this joint probability I need to estimate from data? How many number of cases? In the non-naive case, 2 to the p, right? And for the naive case, how many number of parameters? Naive case, 2p. 2p. Who has question about this? 2 times p. And this just to give you a kind of comparison for the Gaussian case. In the Gaussian case, you need to have p plus p quadratic number of parameters. So this maybe sounds like, why do I need to care about this? Actually, this number is extremely important. Extremely important in the sense of, so really, is my training data large enough to be able to provide an estimation of that size of parameters I need to estimate? It's extremely number you always need to consider. Even for a deep learning model you fit, you need to understand how many parameters you're trying to estimate from the variation. Different model have actually different size of parameter to estimate from the data. All right. Let me try to make this more clear. This is about last time. Discrete random variable. Okay, so let's just now come back to not the general p case, but p equals 2 case. So, okay, so this page is trying to tell you, again, so the mean of the normal PDF is the peak value, which means that position the density is the largest. And the contour of equivalent probability density function forms ellipses. It will be very clear in the next page. The covariance of the normal distribution actually capture linear dependency among the variables. So what does even all those what do they mean? Okay, so yeah, let's see this first. So because in the p-dimensional case, it's much easier to visually see this, right? So let's just see it. So this is the contour plot of a normal distribution. There's only 2 variables. This is the contour plot. So I hope you still remember what we covered during the regression case. When we visualized the loss function or that scoring function j theta, we introduced you can always visualize a function using 2 different views, surface plot or the contour plot. So this is the same thing. Here we are visualizing the PDFs. We are visualizing in the regression, those regression section, we visualize the loss function. Here we visualize the probability density function. In the surface map, so the y-axis, this y-axis is actually the fx1 and fx2. Is that density, probability density distribution, density function. And the 2x1 is, I remember there's a 0. Yeah, so 0 maybe there. So there's one x is x1, the other x is x2. So what you see is the y, actually the y here, representing, or maybe let me write as a y. So this is a y. This y representing the PDF, which shows you there's a peak position close to the mean. That mean vector is at the mean vector is mu. It's a 2-dimensional vector, which essentially is mu x1 and mu x2. Which is that location representing mu x1 and mu x2. Yeah. And then the wideness of the spell representing the sigma, which is illustrated in this page. The sigma here is the covariance matrix. The diagonal term is the variance, representing the variance of the first feature and variance of the second feature. And those off-diagonal terms representing the covariance between x1 and x2. And actually covariance, sigma 1, 2, equivalent to correlation times sigma 1 and sigma 2. And the determinant of the matrix, because to be able to calculate this PDF, you need to be able to calculate the determinant of the sigma matrix, which is a concrete analytic form. So this all sounds pretty difficult and daunting, right? But don't worry. Let's again, so the sigma 1 and 2 really just representing how wide along the x1 dimension, how wide my data distributed apart from the mean of the x1. And sigma 2 shows how wide my data distributed apart from x2 mean. And the contour map here is trying to show you this ellipses, each ellipsis has the same probability density function because they are at the same height. And look here, this is almost similar to what we trying to visualize in the regressions sum of squared error, because that's also a bell-shaped function. Okay, so maybe you can get a little bit in relationship now is, so the reason why people actually work almost the only popular continuous random variable is the Gaussian random variable is it's extremely very well studied function, which is this bell-shaped function. Okay, let's see what does that even what does this sigma 1, sigma 2, sigma 1, 2 even related to Earth, right? Okay, so let's first see what do sigma 1 and sigma 2 and rho, if they differ from a little bit, what does the surface map looks like? So 1 rho, which means correlation equal to 0, right? So let's see the sigma matrix is sigma 1 square, sigma 2 square, rho times sigma 1, sigma 2, and rho times sigma 1, sigma 2, right? Okay. So rho, which means correlation. When correlation equal to 0, the covariance also equal to 0, right? Which means what? There's no linear relationship between x1 and x2. Then its surface map just totally looks like no relationship at all. And because sigma 1 and sigma 2 also is the same value, which means the wideness of how wide the samples in the x1 and how widely distributed of x2, they're also the same. And then this gives us this very nice bell. It's not stretched into some weird shape at all. It's a very nicely rounded bell. So, okay, so let's still keep sigma 1 and sigma 2 the same. But we're doing changing the correlation value to be different, which in this case 0.9, which means the first feature and second feature are nicely positively correlated. And this is the bell shape we learned, which is a very narrow bell, almost concentrated all along that diagonal x1 equals x2 line. This is actual line representing x1 equals to x2. Oh, so this is x1, and that's x2, and this is our PDF, fx. And you can do other similar changes, which is inverse of, you make the rho minus 0.9. Now what would you get? What you're going to be getting is not x1 equals to x2, is the bell is stretched all over this line in the middle, right? So for the middle figure, if the correlation is negative and it's almost completely negative correlated, which means x1 and x2, they're completely negatively correlated, then the line, this bell shape, is not along x1, x2 anymore. It's actually changing to a different, it's x1 plus x2 when x1 changes, x2 decreases on that line. So question about this. Let's just give you visually, what do I mean? Sigma 1, sigma 2, and rho. Yeah, let me actually fix that a bit. It doesn't look good. So because the visually it tells you, and this is the sigma matrix controls the PDF. And the off diagonal term so is the covariance among x1 and x2. Yeah. All right. Now let's see the contour map view. The contour map view is this gives you rounded circle, and this gives you very narrow ellipses along x1, 2, and this gives you another, actually the other direction, 2 ellipses. Trying to show you what's the contours look like when their PDF is the same. Okay, so this is still a little bit lack of direct feeding, right? Let's see the next. Okay, this is actually the trivariate. So I'm going to show you one more. It's what do sample looks like on those contour and surface map. But before doing that, let's see if you have 3 variables and what will your the surface map look like? Actually, this is contour map because there's no way I visualize the surface map when there's 3x and plus 1 because that's 4-dimensional, right? This is actually a contour map when you have 3 variables. It gives you, it's really like a football, right? Very similar to a football and the dimension, and this shows you the correlations among x1, 2, and x3. And so there are a lot of variation. It can be really, really rounded, like a volleyball. It can be really stretched, like a football, and there's a lot of variations there. And this gives you an intuitive view of how multidimensional Gaussian looks like. All right, so I'm trying to tell you all those probability density function, all the description of Gaussian distribution, but in fact, what we truly observe is what? So even though I showed you all those contour map or the surface map, but these are just PDF function, right? What I truly observe is the data. Those data follows the probability density function. And this just trying to show you again, so when you have probability model, and the probability model generating the observed data according to the probability model you actually assume. And from the data, you're performing maximal likelihood estimation to estimate the parameter that determine the probability model. So remember there's 2 directions, model to data, data to model. All right, so I talked of all those models again and again, right? But truly what you observe are data. So what do the data looks like when you have sigma 1 equal to sigma 2 and rho equal to 0? And this is the kind of data you're going to observe. So it's more densely distributed in the center. And the y-ness here, and y-ness here is the same, which actually is the 2. Let's just use 2 sigma 2. And here is 2 sigma 1. And then the rho, because there's no correlation at all, right? You can't see any patterns of x increases and y increases. It covers all the places when x increases, when x1 increases, x2 can be a pretty wide distribution. But when it's the row is very positive, what you're going to observe is not this nice rounded data distribution anymore. What you're going to observe from your sample data, it's quite narrow banded, close to the x1 equals to x2 lines. And then the other one is the one row when it's negatively correlated, and this is the concentrated band you're going to observe. Okay, I hope now this is a really, really detailed now kind of description or review of Gaussian distribution. And by now, you should understand what do I mean, sigma, because they're all representing different sigma, right? Okay, so, and also remember this, when rho equal to 0, and the data looks like that, which essentially means what? Give me so this specific sigma as O in sigma 1, sigma 2, 0, 0 here. So, what does this indicate? Is this a naive distribution or not? Which what I'm trying to see is for the first case, P, actually, let me use F. You actually can easily prove x1, x2 equals to fx1, fx2. Because the covariance is 0, you can just put that into this equation. Covariance is 0, right? You can decompose and then totally decompose this formulation to make it's a product of fx1 times fx2. So you can do this very easily, but I'm not going to do that. So again, I'm trying to show you one is this type of distribution when my covariance matrix is a diagonal matrix, which essentially means my distribution is a naive distribution, which means my joint probability equals to each individual probability times together. Alright, I hope you buy that. It needs a little bit of calculation, but it's actually pretty easy. Just because the sigma equal to 0 in this case. Okay, so this means the naive case, right? So I told you, okay, when I know the probability, you sample data, and this is the case, and you already know the sigma, you know the rho, and you also know the mu, right? So in this case, you can have assumed the mu vector, and then you know the sigma, and the whole distribution is fully determined, and then you sample the data. But assuming you actually do not know, this is the data it's given, this is everything you're given, you need to estimate sigma 1, sigma 2, and rho, and mu from the data to recover the PDF. So this is what I meant, maximal likelihood estimation. You can just use the sample mean and sample variance, and you can prove it. They are the good MLE solutions. So in the high dimensional case, what you do is the same. You just calculate the each mu for each feature variable, the mu for each feature variable, and then you perform sigma. It's just the sample covariance. So I already told you the number of parameters here is p plus p quadratic. We already reviewed before. Then now let's use this type of distribution to perform classification. And that's, I hope you still remember what do we mean generator-based classifier. Generator-based classifier means for each class you have a generator model. And after you have each class for that specific generative, what's the probability of generating that specific sample, then you times the prior of that specific class, whichever the class labels wins out with this joint probability is the classification output. And because we're trying to tell you like a naive version, right? Let's start from the naive version first, and then let's review what do we mean naive based classifier. So naive based classifier, instead of using the full joint probability px1 onto xp condition C, we assume that this joint probability can be decomposed into each feature variable's condition on the class labels. Alright, so this hopefully you also remember very nicely. Then let's use this on the Gaussian case. So first is naive Gaussian based classifier, which is actually very easy. I just told you before, right? So you just write out each feature variable conditioned on a specific class through that equation, and assuming the class label is a specific class label Ci, and then my current feature is Xj, and then its probability distribution PDF, it's just using the formula. The sigma of that feature conditioned on that specific class variable, and then the mu. And because to estimate a Gaussian distribution, so let's see, maybe there's a little bit thing I left is, okay. So for the naive case, if I want to estimate this from data, how many parameters do I need? So to estimate naive, so from data, I need to estimate mu, right? Mu 1 onto mu p. And I also need to estimate sigma 1 onto sigma p. And that's it, because there's no covariance, which means the number of parameters I need to estimate in the naive case is 2p. Okay, question about this. Just p size vector, p size covariance matrix. Okay, so remember that. Then when we use it in the base classification, which means that's for each class labels, we need to have 2p, right? This has 2p, this has 2p onto the 2p. So in total, we need to estimate how many parameters. It's size of the labels times 2p for each class, then plus the prior for each class. And this is the number of parameters we need to estimate in the naive Gaussian case. Okay, question about this. So it's all 2pl plus L. Alright. If the size is linear to the p, similar to our naive base classifier, the number of parameters linear to the p. Alright, so the same thing, you just need to ask the mean, the same thing. So you use sample mean, sample variance, condition on a specific C for Ci. So that's really important. For each class, you estimate sample mean, sample variance, and that create L different generator models. That's the whole idea of generator model, right? For each class labels, you have a generative probability formulation. And on the testing phase, you do the same thing. You just do calculation of C equals to Ci, then Px1 condition on Ci until Pxp condition on Ci, using the equation exactly here by replacing the mu and sigma from the sample mean and sample covariance. All right. Okay, so this is naive assumption, right? I mean, sorry, this. So I hope this is a matrix we normally represent. It's a diagonal matrix. It's a special notation, just diagonal matrix normally represent as this. So like I told you, when you have naive assumption on Gaussian, it's equivalent to, I'm assuming the covariance matrix for that specific C class, because I need to generate multiple sigma matrix, right? Each one of them is a diagonal matrix. So this is what I mean, my assumption, naive assumption. So this is the naive Gaussian classifier, and the total number of parameters, so like 2PL, repeat it. Now let's see the not naive Gaussian base classifier. So one, it's not naive, right? So no assumption, just using the Gaussian distribution. And in fact, we just use the Gaussian distribution by each one of them by consider a subscript C, right? Because for each specific C, sorry, this should be P, we need to estimate sigma for a specific C and mu for a specific C. And we actually talk about it. The number of parameter we need to estimate is the L times the P plus L times P quadratic, right? In versus to the naive case is L 2PL. So the non-naive case has P quadratic more, right? It's like quadratic more, right? This sounds like okay, but in fact, just a little bit larger P makes the P quadratic extremely difficult. So let's just assume, because that's a covariance matrix, right? If we have 10,000 features, then P quadratic number of parameter means what? How many parameters here? 10 to the third, and then it's need to estimate 10 to the 6. Okay, 10 to the 6 is how many? Yeah, it's 1,000,000 parameters. Such a simple model, it needs 1,000,000 parameters for when P equals to 100. Okay, all right. Oh, okay, so yeah, so this kind of repeating, and then, sorry, I mean, okay, I don't even times the L there. So assuming the L equals to 10. So let's just use maybe ImageNet or image problem as example. So roughly P equals to, so I think the generic image size is about 300, roughly 300, yeah. It's the actually 300 times 300, right? The pixel size. The wideness times the height. So what's your current fashion eminence size, each image? 20 times 28. 28 times 28.
Yeah.
Okay, so what is this? 28 times 28?
70.
Okay. It's about 700, right? Let's just make it more dramatic. It's 10 to the 3. Yeah. And then go to P quadratic. How many classes do you have? What's the L?
10.
10. Then how many parameters you need to estimate in this case? Almost 10 to the 7, right? Or maybe 10 to the 6. Actually, 10 to the 6 is more correct. Just to let you know, if you try to train this type of classifier just on the image you are having now, it's about 1,000,000 parameters. And how many samples do you have in your current data? What's the size of your current training data?
60,000.
60,000. Okay. Is it enough to train this size? It depends. Actually, it's not. It's actually fine, right? 60,000 is fine for this size, for 10 to the 7 of number of parameters. Yeah, okay. All right, so just to give you a rough estimation, and So please perform this type of analysis whenever you're doing data. I mean the size n, size p, and also the number of parameters you need to estimate from different models. Okay, so now let's go to the non-naive case, but with some kind of assumptions because p quadratic, there are too many parameters to estimate. Because the data you're having now is, so the p quadratic is still pretty large. The majority of the pre-deep learning era, the size of the training data, in a lot of cases, even smaller than 10,000. So a lot of n actually smaller than 10,000. And for this type of problems, just p just a little bit large, like 100, and L is about maybe 10, and this itself, like LP quadratic, it's about 10 to the 5, 10 to the 4, 10 to the 5, 10 to the 5. So this is 10 to the 4, right? 10 to the 4, and this is 10 to the 5, and it's not going to work, right? So you want to reduce the p quadratic parameter space. And how do you do it? So there are many ways you can do, because first of all, I have to estimate sigma 1 onto sigma L, right? So rather than estimate sigma 1 onto sigma L, the simplest simplification is, okay, I just think they are the same. So this is the first trick. And using this trick, we got the famous classifier called linear discriminant classifier analysis, LDA. The whole thing is just you assume sigma is the same across different classes, which means, so how do you reduce the parameters if you do that? So if you're using the LDA trick, this is called the LDA trick. The number of parameters you need to estimate is from LP quadratic into P quadratic times LP, which is the mean part, the mean vectors. So it reduces all LP quadratic into OP quadratic. This also still have the LP. Just don't get confused. You always need to estimate the mean of each class. All right. So what do the LDA looks like? So we already told you, right? Sigma matrix defines the shape, the contour shape, right? In a two-dimensional case, it essentially means each of my classes is the same shape of the ellipses I'm estimating. So in this case, this is the first class, this is the class L, this is the class K, and this is the surface map view. So they're having the same contour shape, and this is exactly what they're trying to tell, the LDA trying to assume. And there's an indication of when you assume each class, all the classes share the same shape, same kind of shape. It actually means the class decision boundaries are linear. So when I'm assuming sigma 1 equals to sigma 2 until sigma k, it essentially means linear classifier. It's a linear decision boundary you're learning. Yeah, so this just trying to again, sorry, my handwriting sometimes look bad, just, yeah. So again, the number of parameters you need to estimate is sigma 1 vector for the first class, second class until the nth class, and then plus just one shared covariance matrix. And the number of parameters is OLP plus P quadratic. The reason why I'm dividing it by 2 is because of what? It's a property of your covariance matrix.
Symmetrical.
Yeah. So because covariance matrix is a symmetric matrix. So that's why in fact the number of parameters you need to estimate the covariance matrix is not P, it's like P quadratic over 2. And it's indicating you are learning the same shape of Gaussian, the same looking of Gaussian. The sigma is the same, but their center position, their mean position is different from each other. It's the first class mean, second class mean, and third class mean. All right. And I don't want to prove it, but you actually can. I hope you still remember what do we mean decision boundaries. For these decision boundaries, which means PCI conditional X equals to PCJ conditional X, right? This two probability the same, and then you can do this, and that means the density ratio is 1. That means log density ratio is 0, okay? So log density ratio is 0 for those linear decision boundary classifiers, right? All right, now we can just replace PCI conditional X using the LDA conditional probability for and yet you can do all the derivations and I'm not going to do that, and it's actually good, very good proof. And this is what you get if you have LDA. The log density ratio has this format, and I'm setting it to be 0 because like log density 0, log density equal to 0 is the decision points, right? All the decision points of my LDA follows this formulation. And this formulation, this whole thing, because I know sigma, I know the mu, this is just a constant b. And this is X transposition, this is another constant A. It follows a formulation is X transposition A plus B, which is a linear line. You can totally prove it. LDA actually indicates linear decision boundaries. All right, then QDA. So what is QDA? So QDA actually, in fact, is just the Gaussian-based classifier with no assumption. Just if you use Gaussian to represent the conditional probability, the full Gaussian, then that's just QDA. And yeah, so even though there's a lot of description in the literature, in the statistic books, I mean, in fact, it just, you assume each class is Gaussian, and you learn the mu k, learn the mean, and learn the sigma, and you learn the prior, learn sigma, learn the mean, precision, learn covariance, learn the prior, and a lot of cases people actually call this quadratic determinant function, but in fact it's just log of the conditional probability and log of germ probability. Which is exactly that, people just name it with a different name, but nothing special here at all. Alright, so I initially want to do those, but I think it's pretty clear the number of parameters here, it should be L. I should do L because, yeah. Alright, L times P times plus P quadratic. So now I want to compare LDA and QDA. So how to make LDA to be able to QDA in the end, you can actually prove its decision boundaries is a quadratic function. And you actually can also make LDA to learn quadratic decision boundary too. And so this trying to give you a proof, show you it's almost equivalent of function, both learn the decision, quadratic decision boundaries. So let's skip this, and then there's another variation is to combine LDA and QDA. So I'm learning a covariance matrix for each class, but that covariance matrix is also interpolated, augmented with a shared covariance matrix. So the reason is because getting the p-quadratic parameter, it's really difficult to get a good estimation. Then I'm using this shared estimation as a baseline. So really, if you think about this pre-training, all those ideas have a lot of traces here, right? So I'm learning a shared model. Then I'm augmenting each individual models from the shared model. And all those are very similar ideas, and now people pass it to deep learning. And we had a lot of roots in the classic literatures for many years. All right, so my last question actually is naive Bayes classifier learning a linear decision boundary? So where you said, so we have naive classifiers, then LDA, then QDA, right? So the naive one is a diagonal matrix. The LDA is a shared covariance matrix. LDA, it doesn't share, just whatever. And then, because naive is so naive, right? I mean, I have so smaller number of parameters because it's OLP, right? And then here is OP quadratic in terms of covariance matrix. So there must be the decision boundary from the naive version must be simpler. But actually no. The naive Bayes classifier, even though it learns less number of parameters, its decision boundary actually is quadratic. Sorry, I tried to do the derivation, but yeah. So the reason actually, I cannot prove it, but just you remember that as a fact. Okay, I'm pretty slow, but I really want to cover the last part in 2 minutes. So let's compare discriminative classifier versus the generative classifier. So discriminative classifier models Px condition C and PC itself. And discriminative classifier models PC condition X directly. Yeah, so one is this, and this, the other discriminative classifier model PC condition X directly. Let's use a figure to show this. The LDA, or 2 Gaussian, learns 2 Gaussian, right? Class 1 Gaussian, class 2 Gaussian, and then trying to classify the future points according to how likely it's from the first Gaussian or the second Gaussian. But discriminative classifier like logistic regression, it doesn't model each density at all. It only models how likely this part is in the class 1, how likely this part is in the class 0. So that's the differences of what they model. And just to summarize, the LDA versus logistic regression are the most classic 2 cases. Because LDA also learns linear decision boundary, right? So the reason why we put them side by side to compare to each other is because their decision boundary is the same. They're both learning linear decision boundaries. One through a generative formulation, the other from a discriminative formulation. They're all linear decision boundaries. And the most important differences is, let me make this next figure, is you should compare, so when you have infinite number of samples, what is the behavior of your classifier? This is normally called asymptotic behavior. When you have infinite number of samples, what's the behavior of your classifier? Alright, the first proposition is, when you have infinite number of samples, your generalization error, which versus the truth, right? Your prediction versus the truth. The error from discriminative classifier is smaller than the generative classifier. Remember the first. When you have enough data, in this case, it's infinite number of samples. Error, generalization error of discriminative classifier is smaller compared to generative model. But you also can prove the convergence rate of reaching this generalization asymptotic error. So how fast do I converge to that error? The discriminative classifier, in this case logistic regression, it converges using the speed of OP. This means the number of samples. I need the number of samples has the speed is OP. I need more samples to achieve that error rate, which means slower convergence rate. But for the generative classifier, its convergence rate to converge to that best classifier, the asymptotic classifier, is using the convergence rate is log P. In this case, is LDA. So in summary, generative classifier has larger asymptotic error. It converges faster to that error though. And discriminative classifier, in this case, logistic regression, it has smaller asymptotic error, but it converges slower compared to this kind of counterpart of generative classifier. So this figure almost trying to tell you, so when you have really smaller number of samples, the Bayes classifier converges really quickly, very quickly to the better error. The discriminative classifier converges not as fast as the generative classifier when within the smaller number of samples, but when you have larger number of samples, it actually beats the generative classifier to reach better error rate. So I think this is all I want to share about generative versus discriminative classifier. And that I think you should understand empirically it's really this. Generative classifier good for smaller data and also with missing data. It has good way to estimate missing data. And discriminative classifier is good for large training dates. And also it has better generalization error when you have enough data. All right, thank you.